Lecture 44, Fault Reactivation. As we saw before, faulting involves answering this question: will a new fault form, or will slip on a pre-existing fault occur? As shown in this figure, any pre-existing plane whose pole makes an angle between θ1 and θ2 with respect to σ1, will slip. For faults outside these orientations, a new fault rather than renewed slip will occur. In general, pre-existing faults are weaker than intact rocks. The fault has lower cohesive strength C due to fault gouge development. This contributes to lower fault strength as shown by these failure envelopes with 1.0, 0.5, and 0 cohesive strength, C. A decrease of cohesive strength contributes to a larger range of fault orientations, which can be reactivated. This is illustrated by the orange triangle for 0.5 C, and the red triangle for C equals 0. Pre-existing faults also have a lower coefficient of friction. This diagram shows a failure envelope for pristine rock with cohesion C, and 3 failure envelopes for fault reactivation on a pre-existing fault without cohesion, and friction angles of 40, 30 and 20 degrees. As the friction angle decreases, the range of potential orientations for fault reactivation increases. This is indicated by the yellow triangle for phi equal 40, orange triangle for phi equal 30, and red triangle for phi equal 20 degrees. Pore fluid pressures also facilitate fault reactivation. Pore fluid pressures counteract the normal stresses, and shift the Mohr circle to the left. Therefore, they increase the range of potential fault orientations that can be reactivated. This is illustrated by the yellow and red triangles. As we have discussed before, renewed slip on a fault does not occur at the maximum shear stress, but at the optimal ratio between the shear and normal stresses. So, how can we determine the potential for fault reactivation of a fault plane with a given orientation under a three-dimensional state of stress? This is in slide for a previous lecture. Essentially, we can compute the pole to the plane, and the angle the pole makes with σ1, σ2, and σ3. The cosines of these angles are the direction cosines of the pole, in the principal stress coordinate system. We can then use these direction cosines and the magnitude of the principal stresses, to compute the normal and shear stresses acting on the plane, sigma and tau, respectively. The slip tendency is the ratio between the shear and the normal stress on a plane. It is a measure of the potential for fault reactivation. For a given stress field consisting of principal stresses magnitudes and orientations, we can calculate the slip tendency for all possible fault plane orientations. We can then plot the poles to the faults, colored by slip tendency, on both a stereonet and a Mohr circle. Likewise, we can superimpose to these diagrams the pole to a specific fault plane, to evaluate the risk of reactivation on that plane. In the class, we will use Python programming to do this. That's it. To learn more about this, read these sections from Reagan and answer these questions.